Ever wondered how a large language model seems to understand and respond like a human? It's not magic, it's the transformer architecture. Introduced in 2017, the transformer revolutionized how machines process language by letting them consider all words in a sentence at once, not just one by one. Before this, models struggled with long sentences and lost track of context. The transformer's secret? It weighs the importance of every word in relation to every other, capturing complex relationships instantly. The process starts by turning words into numbers, adds signals for word order, and then uses self-attention to connect everything. We'll break down each part of the transformer using simple analogies. No heavy math, just the core ideas. By the end, you'll see how a machine can truly understand a sentence, not just read it. Let's open the black box and see what makes language models tick. Computers don't understand words, they understand numbers. The first step is input embedding. Each word becomes a unique vector in a high-dimensional space, capturing its meaning. Words like king and queen end up close together in this space. But turning words into vectors loses word order, so we add positional encoding, a mathematical signal marking each word's place in the sentence. This signal uses sine and cosine waves to create a unique timestamp for every word. The final vector for each word now contains both its meaning and its position. With both meaning and order encoded, the model is ready for the next step. Now, the sentence isn't just a bag of words, it's a structured sequence the transformer can process. This sets the stage for understanding context. Now comes the heart of the transformer: self-attention. Self-attention lets every word look at every other word and decide which ones matter most for its meaning. For each word, the model creates three vectors: query, key, and value. It compares queries and keys to score how much attention to pay to each word, then uses these scores to blend the value vectors. For example, in "the animal didn't cross the street because it was too tired," the word "it" pays most attention to animal. This process happens for every word all at once, building a rich web of connections. The result: each word's meaning is updated with context from the whole sentence. Self-attention is what lets the model understand relationships, not just individual words. It's the engine behind the model's deep comprehension. But what if a word has multiple meanings or relationships? That's where multi-head attention comes in. Instead of one self-attention process, the transformer runs several in parallel, each called an attention head. Each head focuses on a different aspect. One might track subject-verb links, another causal words like because, another resolves pronouns. These heads produce separate output vectors, each capturing a unique perspective. The outputs are combined and mixed in a final layer, creating a unified, context-rich vector for each word. This multi-headed approach lets the model grasp subtle, layered meanings in text. It's a key reason transformers are so powerful at understanding language. Multi-head attention gives the model a multifaceted view of every sentence. After attention, the model refines its understanding with add and norm and a feed-forward network. Add and norm means adding the original input to the attention output, a shortcut, then normalizing the result for stability. This keeps information from getting lost or distorted as it moves through layers. Next, a feed-forward network processes each word's vector individually, adding extra depth to the model's thinking. Another add and norm step follows, ensuring stability and efficient learning. These steps repeat in every transformer block, helping the model learn complex patterns. Together, they keep the model's representations sharp and reliable. It's the finishing touch before moving to the next block. The real power comes from stacking many transformer blocks, sometimes dozens or more. Each block builds on the last, moving from basic grammar to deep meaning and abstract reasoning. Early layers spot simple patterns. Higher layers grasp themes and intent. For models that predict the next word like GPT, there's a twist: they can't see future words. Masked self-attention ensures each word only looks at previous words, not what comes next. The process words become vectors, get positional info, pass through stacked blocks, and emerge as context-rich representations. Each cycle of attention, normalization, and feed-forward processing sharpens the model's understanding. By the end, the model is ready to predict the next word or generate text that feels truly human. This elegant architecture is the backbone of today's AI revolution. From simple text to deep understanding, it's all powered by the transformer.